We'll wrap up our discussion of the basic Solow model, discussing some of its implications and extensions. For one, we have learned that higher savings do not cause long-run growth. However, when a nation has a higher savings rate versus another, it also has higher level of capital per worker, and hence higher output per worker, much like an increase in the savings rate can cause some transitory growth over time. Now recall that savings and consumption are related. When we think about saving, we also have to think about the other aspect of this model, which is consumption. The more we save, the less we consume today. And the benefit, of course, of this is that we can consume more tomorrow. This in practice then raises the question what an optimal savings rate for a country might be. Now, this is a question of policy relevance because public savings depends on budget behavior. A government cannot control how much households are saving, but if a government runs a budget surplus, it adds to national savings. Meanwhile, if it runs a deficit, it takes away from national savings, and that affects the overall level of investment and hence economic growth. Now, from a growth perspective, what is an optimal savings rate? Now, there are two extremes, of course. We could save nothing at all, savings rate of 0, and that would imply a capital stock per worker of 0 too, right? We haven't put anything away to build up machinery. And because we need capital to produce in the Solow model, this would also imply 0 output. Obviously, that's not ideal. To produce, we have to invest some of GDP. At the other extreme, if the savings rate were 1, we would put everything we produce in capital stock. We would maximize output for that reason. But the problem with that is that we also need to consume, right? If we save everything, consumption is equal to 0, so this too cannot be an optimal outcome. So an optimal savings rate falls in the middle, and it's not one that optimizes production, obviously. It is one that, or maximizes production, I should say. It does optimize production. What it is attempting to do is it's trying to set the capital stock just so that our steady state level of consumption per worker is optimized. That would be an optimal savings rate. There are a few things we're ignoring here. Specifically, we're ignoring discounting behavior and timing. This idea that if we consume something today, it's a little bit more valuable for us than something in the future. But the basic model illustrates the trade-off appropriately. Now, the savings rate, which maximizes steady-state consumption, is referred to as the golden rule of capital. It's sometimes named it was named that originally by Edmund Fels, I should say. It's usually referred to that. It's a little bit simplified in the Solow model. In reality, the optimal level of capital is somewhat lower. And the reason for that is that we discount, as I mentioned before. But in terms of the actual modeling logic, ignoring that only makes a pretty marginal difference. And it saves us a lot of higher level calculus, which is the reason why I'm not going to go into this. Now, how do you get that? There's a little bit of algebra here, but it should be relatively straightforward. Consumption per worker is equal to output per worker minus savings per worker at any point in time t. Of course, output per worker minus savings per worker is the same thing as output per worker minus the savings rate times output per worker. That's how savings is defined. And then we can plug in the production function where we get lower f kt over n minus s times f kt over n. Right? This is just our consumption. Now, in the steady state, we also know that savings need to equal depreciation. Right? We showed that in the last deck. If you can't recall that, you should probably go back and review that aspect. Now, substituting the steady state level of saving into the previous equation gives us an expression for steady state consumption. Specifically, C star over n is equal to f of k star over n, output at the steady state, minus depreciation times k, the rate of depreciation times k star over n. And the reason why we can plug this in here is that at the steady state, investment saving is equal to depreciation. Now, how do we get from here to an optimal level of capital? The way you do that, the easiest way to do that, is to take the first partial derivative of this function with respect to k star over n and then set it equal to 0. There's a little bit of calculus. If you don't recall that, what you're doing here is you're trying to find the level for which the slope on the consumption function is flat, in essence. That will be an optimum depending on the function that you specified, but under the assumptions we'll make, it will give you an optimum for sure. It will give you a maximum. If you do that, what you find as an equilibrium condition is really not the right word, the optimality condition for k star over n is the level of steady state capital for which the marginal product of capital equals the depreciation rate. Graphically, if you go back to the graph, if you compare the production function and the depreciation line, that will be the level of output for which the two are the furthest apart. That's really what this condition tells you intuitively. Now, by substitution, then we can also show that there is something like a, how should I say, the golden rule savings rate. The golden rule savings rate is defined as the steady state level of depreciation at the golden rule level of capital divided by output at the steady state for the golden rule of capital. Now, why do we get there? This may not seem intuitive right away. The general idea here is that savings needs to equal depreciation in the steady state, made that point before, and savings over output is your savings rate. So if you know what your depreciation is for this optimal level of capital that we found in the previous equation, and if you know that level, you can find output, you can find the savings rate by dividing one through the other. Now, why does this matter? Um, as I mentioned earlier, countries have perhaps excessive or insufficient savings. This is an ongoing discussion. So, for instance, in the US, over a long time, savings have been relatively low. If you compare this with a country like Japan, savings there are much higher. And this is a discussion of policy relevance, usually comes up in the context of Social Security reform. Social Security currently is a redistribution from one generation to the other. So the working generation contributes, it pays out the benefits of the retired population. And needless to say, that doesn't create any sort of savings at all. So every now and then there's a discussion about whether we should privatize at least some aspect of Social Security. And what that really means is that the current generation would have to pay in a certain fraction of their labor income that gets invested, that gets really put into savings. And then when they retire, they could take some out of it. There are some practical considerations why this might not actually work because it's not really clear how we would switch from one system to the other, which I'm not going to go into. But the general idea is that if you privatize at least parts of Social Security, it should increase the savings rate in the United States, which in principle might bring up the steady state level of consumption. That is, of course, an empirical question, but at least that's the economic argument out there. Now, I'm going to leave it at that. This is something you should be aware of. As I said, there is a bit of discussion around this. Currently, we're not discussing it because we have a bigger fish to fry. But be aware that there is some policy relevance to even this very basic Solow model. Now, with the Solow model done in its basic version, we really haven't learned what causes growth. We've just learned what doesn't cause growth, and that's capital accumulation or factor accumulation more broadly. Now, a variation of that, which is in the book as well, is the so-called AK model. I will probably post some optional notes on this. I haven't quite decided that yet. I will keep you updated with announcements. What the AK model does is adds two complications to the model I've just gone through. The first is adds population growth. And the intuition here is that a higher population figure, an expanding population, all else the same, reduces the amount of capital per worker. So for a steady state to be feasible, as we've just discussed, the capital stock per worker needs to be constant, which means capital has to grow at least at the rate at which the population grows. Now, that is a thing that you might be aware of. When economists think about long-term potential growth of GDP, they factor in population growth, and that is the reason why. As long as the population is expanding, we can add additional capital at the same rate, and the marginal product of capital will stay constant as well. If we are not doing that, the marginal product of capital will actually rise, and that again gives an incentive to invest more. That's the impact of population growth, intuitively said. You can also go through that formula and you will see it's the same result. The second thing that the AK model adds is a factor A that is referred to as total factor productivity. And what total factor productivity captures is the cumulative effect of technological growth. This idea that while we have the same resources because we develop new technologies, we can produce more at the steady state. And the change in A is what is usually referred to as the rate of innovation or the rate of productivity growth, total factor productivity growth, which means that for the same level of output per worker, with better technology, we can produce more. The same level of education or land or other natural resources, we can produce more. And technology is a bit weird because what technology really is, it's a body of ideas. Right? So the assembly line per se is not a physical thing, it's a concept. And because there are no physical constraints on such concepts, the law of diminishing returns doesn't grasp in the same way, right? Even if we are employing a limited amount of production factors because there's the law of diminishing returns, if we come up with better ideas to combine these factors of production, the economy can still grow. So when you think about potential growth, when economists think about that, the two factors they will always take into account for GDP overall is population growth and productivity growth. Right? In that sense, the idea of innovation as productivity, not so much labor but productivity like we've defined it just now. So in the United States, when I earlier talked about these productivity estimates of economic growth, uh, this is what we really have in mind. An economy at the steady state at capacity can still grow if its population is growing or if technology is increasing. And for the S, the estimate is about 2%, perhaps a little bit higher because total factor productivity is not that easy to measure. But that's the rate of sort of long-term growth that we're looking at. It's rooted in these two considerations.